So 5.5, so this section here is where we're going to be learning about how do I choose what numbers to use synthetic division with. We've been doing synthetic division, but we haven't seen an example of where I don't tell you what to divide by, you have to find that number yourself. So that's what this lesson is going to be about, is how do I generate the numbers that I need to potentially use synthetic division with. All right, so here it says if you divide a polynomial by x minus a, we typically see those in parenthesis groupings like that, then PA must be the, so with that, all right, so we're looking for where a is we call it the root sometimes, other times we call it x-intercept, sometimes we'll call it a solution, and then we'll sometimes call it a zero. And that's the one that kind of makes most sense in terms of this, where it's talking about P of A here. We want P of A to equal 0. All right, but those other words are the same, or synonyms, right? Because x-intercept, the y-coordinate is 0. All right, and so this is just what allowed us to determine if we should use synthetic division or not. So for this one, it wants to plug in x is 3. And we'll see, will it in fact equal up to a 0. All right, so we're going in here, we're plugging in 3. No, is that what we're plugging in? Yeah, 3. Okay, so 3 to the 5th is 243. And we're subtracting 3 cubed is 27 times 2 is minus 54, minus a 9, plus a 2. Now you might be able to see just by using common sense math that this will not equal 0. So at that point, it doesn't even matter what it's equal to. It's in the 100s somewhere. But since it's not 0, that would not be a factor. All right? And so that was the remainder theorem that we were using at the end of 5.4, part 2. So on this one here, if we were to go through and plug in that number, 38x minus 240, and we're plugging in negative 5, we get here a negative 125, and that would be negative 5 squared is positive 25 times 7 would give us 175, and here we get a positive 190 minus 240. And if you type in all that into a calculator, you realize that P of negative 5 is equal to 0. And another way of viewing this is it's just like function notation. It's saying that negative 5 comma, the result, is equal to 0. So just like this one up here, we didn't find it yet, but 3 comma. All right, if we finish calculating this one, it lands at a 182. So this is basically function notation. Plug in your x, and it tells you what your y-coordinate is. All right, and so if you get a remainder, it's obviously not an x-intercept because this one's super far up in the y direction. This one would be. All right, so roots are found when y equals 0. So in other words, we hope to pick the correct x value and then plug that in to get 0, and then we know that's our x-intercept. However, when solving an equation like this, 24x cubed minus 22x squared minus 5x plus 6 is equal to 0, it can be difficult to figure out what x values would give us x-intercepts. So there's a theorem that's going to help us do it. Now this is just a tool. It's not the end-all be-all way to do this. We'll also cross-reference it with our graphs. But it is interesting to kind of look at where this comes from and why this works. It's going to generate us a list of possibilities of which could be our x-intercepts. All right? And so we're going to equate some names here. This 24 is what's called the leading coefficient. All right, because it's the number all the way out in front. And then the 6 at the end, that's called the constant. Okay. And what we'll be doing is we're going to take the factors of the constant. So we'll actually start with the number on the end. we'll take the factors of the constant, divide it by the factors of the leading coefficient, so the number out front, and then that list is going to tell us all the possible values, and there'll be a plus or minus out in front of it, which kind of doubles everything. But let me explain kind of how this operates and why this will work. And here's what it's going to look like over here. You'd have a plus or minus. Here would be the factors of the constant. And in the denominator, you'd have your factors of your leading coefficient. Okay. So let's see why this works. I'm just going to make one up. May or may not be factorable. But if I gave us something like this, like 2x squared minus 7x, you don't have to write this part down, plus 32. All right, now when we would think about factoring this leading coefficient dictated what would go in these first two slots, right? And in this one of them would have to be a 1 and the other one would have to be a 2. They couldn't be anything else. They couldn't be a 3 or a 5 because none of those would multiply together to get me a 2. Now numbers that go here in the end slots would be factors of 32. So it could be 1 and 32, 2 and 16, 4 and 8. Lots of different options there. So the reason we don't care about any of the terms in the middle is because it's just the factors of the first number and factors of the second number that dictate what could possibly show up in our parentheses. Then once we got it factored, it would just be whatever's inside those parentheses equal to 0. So it's only the factors of the first and last number that really matter. All the stuff in the middle just kind of comes out when you FOIL it. So that's why it works. And just like with factoring, sometimes there'd be a whole bunch of combinations and possibilities. Let's take a look at this one here. So we'll set up our equation. Well, not equation, our formula. So plus or minus, and we need to look for factors of 6. So I could do 1 and 6. I could do 2 and 3, and then 6. You kind of just basically write out, starting at 1, going up the list, would that number divide 6 evenly? And then we'll want to do it for our 24. So 1 goes into 24, 2 does, 3 and 8 does, 4 and 6 does, 7 doesn't, 8 doesn't, 9 doesn't, 10 doesn't, yeah. And then so we got 12 and 24. All right, so this one has a giant list of possibilities. Now, I'm not going to make us list these off very often, and if we do, it's not going to be a ginormous list like this one. We're not actually going to list this one out because it would take us at least 3 or 4 minutes. But the way you generate the list is as such. You just basically create all the different fractions for each possibility. So we've got plus or minus, and then we'd find all the different combinations of 1, which would be, so we'll list out the 1 just so you guys can kind of see what it looks like. It'd be 1 over top of all those different numbers. All right, so it would be plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 3, and then just taking that 1 and putting it over top of all the different denominators. All right, plus or minus 1 over 12 and plus or minus 1 over 24. Now that's just the one for the ones. You then have to go back and look at the 2. Now some of them would overlap, but like 2 over 1, that one would be unique. But then I'd have to do 2 over 2, which is just a 1. 2 over 3 would be unique. And so this would just go on and on. There'd be quite a large list here. Because I'd do kind of following the highlighting here. I'd have to do 2 over 4, 2 over 6, 2 over 8, 2 over 12, 2 over 24, which I think all of those are repeats out of what's here in the first line. But there'd be other distinct ones in there too. For example, when you started to look at 3 and did 3 over 1, 3 over 2. So quite a large list of possibilities. All right. So when it's this large, the formula is not super helpful because there's just so many on the list. Now, in the old days, before graphing calculators, people would have to generate this list and then just start picking them. And keep in mind, they're all plus or minus, so they're technically twice as many as it appears. They'd have to start picking different values, plugging it in like we did up here, and trying to find which ones landed at 0. So if you guys went back in time, like 50 years or however long it was, I guess graphing calculators aren't nearly that old because computers aren't either. So if you guys go back maybe just even 20 years, be quite a different way and approach to take this chapter down. So chapter got a lot easier with graphing calculators, because what we'll do is we will type this in and just look visually where does it cross over on the x-axis, and we'll still be able to cross-reference it with this, which is nice. And it's just a tool, right? It's just another way to kind of double-check your work as you're going. But let's do another one here, and this one won't be quite as long, and then we'll talk about using our graphing calculators to kind of find these. All right, so remember, it's factors of the numbers on the end, which we've got factors of 5. It's just 1 and 5 in this case. Factors of 2 out here in the front. It's just 1 and 2. So this list is much more manageable. Let's do the ones first. We'd have 1 over 1, so plus or minus 1, plus or minus 1/2. Then we do it with the 5. So we'd have plus or minus 5 over 1 and plus or minus 5 over 2. So a much smaller list on this one. So what these numbers are telling me is if this polynomial crosses over the x-axis, they will have to be from this list of numbers. So I won't be expecting an x-intercept of, say, 7, because 7 doesn't show up on the list. These have to be, if there are any, these have to be the spots that it crosses over from this list. All right, so at this point on the recording, you have to type in your polynomials, and you can verify visually that if you graph this one, that the spots it does cross over the x-axis with either second trace 0 and then going through the left bound, right bound guess, or just hitting regular trace, typing in these values and seeing which ones get you to have a y coordinate of 0, either one of those. So if you looked at these on the graphing calculator, you'd see that the spots where it crossover had to be these. So you can expect on future quizzes or tests to maybe have to make a list of this size, right? Because that's not that big of a deal. And you need to know how to generate the numbers. I'm not going to give you one of that size because first off, I don't want to check and make sure that people have all like 70 of them there. And this kind of demonstrates do you know the concept or not. All right, so how does this help us? So once we find, now it's right here, I'm going to change this up a little bit. Once we find possible roots, all right, you can then use our synthetic division to divide them out, and that's what's going to help us factor. So we would find those possible roots. We then go to our calculator, see which roots are the actual ones we want, and then we can take those values and use synthetic division. And that's what we're about to do.